Hey there, welcome to another video. I hope that you're doing well, and I hope that you watched the last video on what radians really were, because what we're going to get into is how to convert between degrees and radians. Why? Well, because both units of measurement of angles are very important and they're used in real life quite often. A lot of our math is going to be geared toward radians. A lot of real life stuff is geared toward degrees, and we have to be very comfortable and confident with using both of them. And so what we're going to do today, right now, is learn how to convert between radians and degrees. If you've ever studied radians and you've heard of them and you really didn't know, hopefully you watched the last video, didn't really know what they meant, hopefully now you do. Hopefully you understand what a radian is, this idea of the angle that's needed on the center of a circle to sweep out an arc length or cut or subtend, an arc that is equal to the radius. That's it. That's all it is. It's different than degrees, and a lot of formulas only work with them. So, but if you understand that, or maybe you didn't understand that, and you've seen some of the radians, like what does pi over 3 mean? Why do radian type measurements have a lot of pi's in them? Why do we get that? Why do we have this, man, we get 3 pi over 2 or whatever we have, or 2/3 pi or 2 pi over 3 or negative pi? Why is pi so involved with radians? We're going to find that out today. So let's get started with it. What we learned last video was that if we have an arc length that's cut by some central angle theta, we can determine what that arc length is. Or if we have a radius and an arc length, we can determine the angle that's needed to get that particular arc length. And we had a formula. And we made a big note that said, this is only for theta radians because there is a 1 radian idea built into that proportion from when we did it last video. So I hope you watched it. I hope you remember that. We did a couple examples, not too many of them. We're going to get to some applications in a little bit. But let's come back to an idea. Let's come back to this idea of arc length is proportionally related to the central angle that cuts it. What if we took this circle here with a radius of, who cares, just r, and we went not just a little angle, not just a big central angle, but a full-on rotation around that circle. So if we went and measured this counterclockwise, so positive, and it sweeps out 1 entire revolution. So our theta here is the central angle that terminates the radius where it initiated, hopefully on the positive x-axis, we swept out the whole thing. Well, then what would the arc length be? Well, the arc length would be s, and we'd say, okay, well, we know a couple things about this, right? We know that arc length equals r times theta, but we know a little bit more. We know that arc length is also the full circumference of a circle here. So this is kind of cool. This says if we sweep out an entire central angle that represents 1 full rotation, it terminates where it begins, it's going to have an arc length of the entire circle, which is the circumference, and that's what that angle represents. Well, then we can keep on going and we can say, hey, that arc length, we know circumference of a circle, in this case, would equal arc length. But circumference of a circle is 2 pi r, which says that in this particular case, if we allow that central angle to be the entire circle there, then 2 pi r would be our arc length, the circumference, and that would equal r times theta. Now here's what this means. Watch very carefully. Remember that theta is in terms of radians. It's always radians for this formula. We just used this formula. We just said, hey, imagine this theta is the entire swept out portion of that circle. It makes 1 revolution. Then the arc length is the entire circumference of the circle, but we know the circumference. Circumference is always 2 pi r. So if the arc length is the full circumference, the circumference is 2 pi r, then 2 pi r has to equal r times theta radians. And we're going to remember that this was over 1 radian. That is why this had to be only in radians. So if we remember that, we understood that this had to be in terms of radians to cancel it out. Well, if we want to divide by r, which we can certainly do because r is not 0. If r were 0, we wouldn't have a real circle. We'd have a little dot. We had that which hath no breadth. It would not have this idea of a circle to it. So provided that we have a real circle here, we can divide by r, and we can get 2 pi, r's would cancel, equals theta over 1 radian. Let's multiply both sides by 1 radian. And here's what this means. I hope that you followed me. I hope that you saw that if we sweep out one entire rotation of a circle, and that is our angle, the central angle represents that entire circle, and our radius here is r, our arc length is going to be the entire circumference of a circle, which we know to be 2 pi r. So arc length is circumference. We know that arc length also equals radius times theta in terms of radians. If we divide by r, we have that there are 2 pi radians in one rotation of a circle, one full circle. Now, that's impressive, but it's also where all that pi junk comes from. So when we see, oh man, when we work with radians, it's always pi over 3, or pi over 4, or 5 pi over 6. Why does it always have pi in it? Because of this, right here. Because of circumference, actually. So because circumference represents that entire arc length, and we divide both sides by r, we get the central angle needed to represent that arc length. Well, the arc length, the central angle is now 2 pi because of that circumference. And everything that we do that cuts that angle smaller is cutting the circumference, not circumference, but arc length smaller. And so it's based on a proportion of 2 pi. Let's say that again, really to sink in. Because the full circumference is 2 pi r, and hence we get the central angle is 2 pi, anything that has a smaller angle will have a proportionally smaller arc length, but that's based on the circumference of 2 pi r. So it's a proportion of 2 pi for the central angle that we're dealing with, which is why those radians always have pi in them. Almost always have pi in them. It's because of that reason. So I hope that you're seeing that connection. It's not magic. It's just the circumference. That's it. And we're taking parts of it to create central angles smaller than the theta creates the arc length of a full circle. Let's go ahead and let's go a little further. But wait a second. One full rotation of a circle contains 2 pi radians. We also know something. We know that one full revolution of a circle is 180 degrees. Sorry, 360 degrees. If one full revolution is 2 pi radians and one full revolution is 360 degrees, then those two things have to be equal. They both represent the same exact measurement of an angle that has the circumference of a circle. I hope that makes sense to you. It should be kind of straightforward, I suppose. One full revolution or rotation, or whatever you want to call it, had 360 degrees. That was the definition of what a degree was. 1/360th of a circle or rotation or revolution. But we also found out that there's 2 pi radians in that same measurement. So they must be equal. And this gives us a way to convert between radians and degrees. Just depends on what you want to solve for. So if we divide both sides by 360, we would get 1 degree. We can simplify that a little bit. So 2 and 360 have that common factor of 2, so we can reduce this to pi over 180. This is actually how we convert between degrees to radians. If we understand that 1 degree is pi over 180 radians, that's pretty small, right? Because think about that. Pi would be half of a circle. And if we divide that into 180 little parts, well, 100, that's pretty little there. 180 little parts, that's going to be 1 degree. So pi over 180 radians is that 1 degree. Now, what if we divided both sides by 2 pi? Well, then we're going to get 1 radian equals into this terms of degrees. So let's divide both sides. Here's one way, divided by 360. Let's divide both sides by 2 pi. With a very similar simplification, we would get 1 radian equals 180 degrees over pi. Or 180 over pi degrees is a good way to state that as well. So 1 radian, this thing that represents, this central angle that represents an arc length being equal to the radius, that 1 radian is equal to 180 degrees divided by pi. That would be the degree measurement it would take for a radius to equal a subtended arc length in any circle that we have. These are also the ways that we go ahead and convert. We're going to practice a couple in just a second, but I want to get you used to 2 different starts of a unit circle. We'll talk about unit circles in a little while. If you've ever seen one, I'm going to show you where they come from and a very easy way to remember it, because you'll want to memorize it. You'll want to not have to always look back at a unit circle, even though a teacher might give it to you. It's really nice to have it down. And so we're going to learn kind of 2 different types of unit circles, one based on degrees and one based on radians, because they need to be interchangeable in your head because we use both of them. So how we started with an XY axis or coordinate system, we said this initial side always starts on the positive x-axis, and if our terminal side ends right where it initiates, we'd have an angle of 0 degrees. Or if we did 1 full revolution or rotation, we would get 360 degrees. If we went to the first quadrant angle, we would get 90 degrees. Second quadrant angle was 180 degrees, 270 degrees, and we also know that we could measure clockwise negatively. So negative 90, negative 180, negative 270, negative 360 degrees. I'm not going to show that, but that was something that we could do. Now, what happens if we have these radian measurements? Well, if we have let's think about what this comes from. If we have no angle being swept out, then that idea of, hey, your terminal side doesn't move from your initial side, there's no distance between them, so to speak, then you still have an angle of 0, whether you have radians or whether you have degrees. So we'd still have 0, but it'd be in terms of radians. Don't put the degree there. Now, what would happen if I go all the way around the circle, 1 full revolution? Well, we learned that right here. We said 1 full revolution is equal to 2 pi radians. So on this different type of way to represent our angles, you'd have 0 or 2 pi for the positive x-axis. But they're in terms of radians. Now what happens, let's think about this, what happens if we go to half of a circle? Well, think logically about that. If 1 full revolution or rotation is 2 pi, then half of that would be 2 pi over 2. Well, wait a minute, 2 pi over 2 would just give us pi. So the second quadrant angle there would be pi. Pi and 180 degrees are equivalent units of measurement for your angles. That's kind of what it says here. Pi over 180 and pi over 180 over pi represents like this idea of 1. It's the same thing when you're comparing those measurements, degrees and radians. Now, what if you did only a fourth? So we know that 1 full revolution was 2 pi. We already studied that. We said if we cut that in half, that'd be half a revolution, that'd be pi. But what about half of that? What about a quarter of a revolution? Well, it seems that if this is pi radians, half of that would be pi divided by 2, and that's exactly what we get for that positive y-axis there. It will come about that you will memorize that 90 degrees and pi over 2 mean the same thing, and they do. Whether you have the first quadrant angle represented in degrees, which is 90, or the first quadrant angle represented in radians, which is pi over 2, they mean the same thing. Now, what about the last one? Well, if we count by pi over 2's, that might be a good way to go. So 0 pi over 2, 1 pi over 2, 2 pi over 2, which would be 1 pi, or 3 pi over 2, And if we go a little bit further, we get 4 pi over 2. But 4 pi over 2 is 2 pi. That's exactly what we can do here too. 90 plus another 90 is 180, plus another 90 is 270, plus another 90 is 360. Pi over 2 plus another pi over 2 plus another pi over 2 plus another pi over 2 gives us every one of those quadrant angles. This is what I'd like you to know. I'd like you to know what the quadrant angles are, whether we're talking about degrees or radians. It's very valuable. It's going to start us off on what a unit circle is in just a couple more videos, and then we're going to use that for basically the rest of our math lives. You're always going to be coming back to a unit circle, or at least have it in your head and understanding the translations between them. So I hope this has made sense to you so far. We're going to come back and I'm going to show you some conversions between radians and degrees. But at this point, we really need to understand the interplay between what a circumference of a circle is, the fact that this arc length is that circumference, and this is the reason why we get a lot of pi's in our radian type measurements. So I hope it's making sense. I'll see you in a little bit for some conversions. Now that you have hopefully a good idea about where the conversions come from between degrees and radians, radians, degrees, we're ready to do a few examples. I know that I probably could have just given that to you and you would have been fine, but a lot of times students do not understand why radians have pi in them. And I really need you to see, I wanted you to see and understand that it's based on the circumference of a circle and proportions thereof. And that's where that comes from. So now I'm going to show you how to use this. We're going to go from degrees to radians. That's typically a little bit easier to do as far as understanding where the quadrants are, because we're more used to degrees. And then I'm going to show you a nice way to count with radians. I'll show you exactly how to do that. So let's go ahead and get right into it. If we ever have to convert from degrees to radians, here's the idea. 1 degree is equal to pi over 180 radians, and so that's substitutable. And so what we're going to do every time we change from degrees into radians, we're going to show that. We're going to show that, hey, 60 degrees is the same thing as 60 times 1 degree. But because we know 1 degree has the same central angle measurement as pi over 180 radians, so remember, pi is 180, it's a straight line. The angle of a straight line is 180 or it's pi. If we divide that into 180 parts, well then we get what 1 degree really represents. And so we'd say, okay, this is 60 times 1 degree, but because 1 degree is pi over 180 radians, we can make that substitution. You're going to really like it when your numerator and denominator is simplified. It's going to give you what are nice for radians. And this is what happens here. So I'm going to start trying to introduce some of the very common radian type measurements for us to get used to them. So 60 divided by 180, well, that's going to be 1/3. And so we have pi over 3, and we typically write that way. We usually don't see 1/3 pi. We see pi divided by 3 and simplified fractions within that. So 60 degrees is the same. It's the same thing as pi over 3. Now, I really want to start thinking about the quadrants also. We need to be very good at understanding that 60 degrees and pi over 3 represent the same thing, and they're in the same quadrant. So 60 degrees, very nice on this sort of degree-driven unit circle, which is where we're going, or degree-driven XY plane. So 60 degrees, we probably understand that's somewhere between 0 and 90, closer to the 90. Can you do the same thing with pi over 3? The answer is yeah. I'm going to give you the way that I think about this. Here's what I understand about it, and hopefully this works for you too. If I know that pi represents this straight angle, is what they call that, or the second quadrant angle. If I understand pi represents that, I always think about my straight angle, like the upper half of my XY plane, and I cut that into whatever my denominator says. So my denominator says, cut that into 1, 2, 3 parts. So first part, second part, third part. I've got a picture in my head now. My numerator says how many of those parts to count. So remember, 1 part, 2 parts, this would be the third part. My numerator says count 1 of those parts. Well, I know I haven't made it past halfway yet, so that's going to be in the first quadrant still. That's how I always do it. So again, I take my straight angle, that represents pi. Remember, that is pi. My denominator cuts it, my numerator counts it. For me, that's the easiest way to go about do it. I don't make mistakes because of that. And I would think, okay, this would be 1, 2, 3. I'm sweeping out numerator, one of them. That's the same exact quadrant, same exact angle as 60 degrees, and get used to it. That those are the same and they're interchangeable. Now, how about 150 degrees? 150 degrees, well, we can write that as 150 times 1 degree. But because that degree is pi over 80 radians, 180 I should say, we can simplify it. It's not as nice, but remember that 150 and 180 are both divisible by 10 and 3, so that means 30. So that would be 5 over 6. Now you can divide both by 10, get 15 over 18, then divide both those numbers by 3. That also works. You get 5 over 6. Either way, we get 5 pi over 6 radians. You know what? As some students, they just hate to simplify these things. Just leave it. You can. It's not appropriate, but you can leave it. And it does mean the same thing. But think about this. In order to count that, would you really want to divide that up into 180 parts and count 150 of them? Or would you rather divide the straight angle by 6 and count 5 of them? Well, that's a little bit nicer to do. So let's look back at this, figure out the quadrants for both of these angles the same angle represented 2 different ways. 150 degrees, yeah, that's going to be somewhere between 90 and 180. 60 degrees past 90, 30 degrees from 180. So that's going to be closer to the 180 than the 90. Well, now let's think about how that would affect our movement or our terminal side on our radian-driven xy plane. So 5 pi over 6, here's what I think of. Here's my straight angle of pi. If I divide that into 6 parts, that would be 1, 2, 3, 4, 5, 6. So 3 parts would equal that pi over 2. 3 parts of 6 is halfway through. So I'm going to count 1, 2, 3, 4, 5. Or 1, 2, 3, 4, 5. That gives me the same angle as 150 degrees, but just in terms of radians. So I know both of them, because they're the same, end up in quadrant 2. Just getting in the habit of thinking of that. So that pi represents straight line. Denominator cuts it. Numerator counts it. Hopefully that helps. It always helped me. How about negative 45 degrees? Well, negative 45 degrees, we know that measuring clockwise, 45 degrees is right between 0 and negative 90. So we're going to be in that quadrant number 4. If we convert this to radians, it should yield the same result. Notice how the conversion between degrees and radians has nothing to do with the sign. So whether you measure degrees positively or negatively, you're going to measure radians the same direction. So negative 45 degrees, negative 45 times 1 degree. We know that negative 45 times 1 degree can be represented as that pi over 180 radians. And if we simplify that, well, 45 and 180. 45 goes into 180 how many times? 45 goes into 90 twice. 90 goes into 180 twice, so it's 4 times. This would be negative pi over 4. But now we're talking about in terms of radians. So let's think. Negative means I'm still going to go clockwise. Pi over 4. All right. Well, if I think about this as pi, then pi over 4 would cut that pi over 4. That 4 would cut that into 4 pieces. So here's my pi, my straight angle. I would count 1, 2, that would be halfway through, and then 3, 4. So my 4 pieces are here, 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 and here. Well, I'm counting now just one of them. The denominator cuts it, the numerator counts it. So this would cut 1 part, 2 parts, 3 parts, 4. I'm going to count down one of them. That's still in quadrant 4. That's the same exact angle as negative 45 degrees, represented a slightly different way. Last one, 107. This is nasty. And when you simplify it, it's not going to work. In that case, it's okay to use decimals, but we start running into an issue of how to represent that on a unit circle or XY plane that has radians. I'm going to show you that in just a second. So 107 degrees would say, all right, well, 107 times 1 degree. We know we're measuring counterclockwise. We know that we're past 90 by 17 degrees. So that's just about right there. So we know we're in quadrant 2. And we would get 107 pi over 180 radians if you didn't simplify it. And it doesn't simplify it. But that's very hard to think about. Why? Because you'd have to think of 180 little parts on a straight angle and count 107 of them. Well, that ends up being exactly 17 degrees past 90. In which case, this would be a better way to go. Like, you'd think about it a little bit easier. When that happens and it doesn't simplify, it's appropriate to use a decimal. I think I got 2.8 or something like that. Oh, sorry, 1.868. So on your calculator, just do 170 times pi show, pi button divided by 180, and you get that 1.868. Now, how in the world could we get 1.868 in terms of radians on that? You go, I don't know, that's all in pies, this is not pi, so what in the world? This is in radians though. So think about it. If pi is, you should know pi. You should know that pi is approximately 3.14. All right. Well, half of 3.14 is what, 1.57? So half of that, this is 1.57. 1.68 is past that. That's one way that we can start thinking about where these radians lie, even if we don't have the pi. I'm restraining myself from making jokes about rhymes, but I have to. So that 1.86, well, that's past that 1.57, so that would still be in quadrant 2. Now notice how that was a bit more difficult to deal with, right? Because you had to approximate a lot to get there. And that's what we have to do when we can't simplify and have it in terms of some sort of a nice denominator to cut our pi into. That's where 180 is divisible by our denominator. That makes things nice. And that's going to yield some very nice things for radians. If your 180, your pi, is divisible by your denominator, that's a nice thing to be able to deal with. Anyhow, what if I had like 90 degrees? So we should understand this, that we've already kind of done it. If I'm giving you 90 degrees and ask you to change to radians, it's a really easy conversion. You're going to get pi over 2. The reason for that is because if we have 90 over 180, we're going to get a denominator of 2. And that's going to be a nice quadrant angle for us. You don't see that super often. We're going to see it here, but that can happen. Now let's go backwards. What if we have radians and we want degrees? Let's give that a try. All right, so we know that pi over 6 radians is a radian type angle measurement, but we also know what 1 radian is. 1 radian equals 180 degrees over pi. So we can go about the same conversion, just backwards. So pi over 6 radians is the same thing as pi over 6 times 1 radian. You're taking a fraction of that radian. But 1 radian is 180 degrees over pi. And lots of things are going to simplify. It's kind of fun. Kind of like doing the pi's are gone. Woo! And 180 divided by 6 is going to give you, well, it's going to give you 30 degrees. Can we determine where both of these lie? Well, pi over 6 means 1 out of that pi cut into 6 parts. So if pi is our straight angle, and we're going to cut that into 6 parts, denominator cuts it, numerator counts it. Cut it into 6 parts. 1, 2, 3, 4, 5, 6. Now count one of them. Oh, that's right there. So denominator had cut into 6 parts, and the numerator just counts it up. Just counts one of those 6 parts. That's going to be a very low, not very low, a lower angle closer to 0 than pi over 2, but your angle certainly being quadrant 1. Think about 30 degrees. 30 degrees is 1/3 of this distance, just like this was 1/3 of this distance. So 30 degrees closer to 0 than 90. That's the same angle. They're both in quadrant 1. Let's keep on going. How about 3 pi over 2 radians? Now, if we're in radians, we go through the same conversion. We can still take that 3 pi over 2 times 1 radian. 1 radian is the same thing as 180 degrees over pi. Pi's will simplify. I would probably do 180 divided by 2 and then multiply by 3, but you have a calculator, it'd be kind of nice to do a fraction times 180. Either way you go, you're going to get 270 degrees. And we kind of should see that, right? Here's 3 pi over 2, that's quadrant angle. Here's 270 degrees. It needs to be the same, and we see the math here that it does. It does equal the same thing. Don't forget to put the degree. How about negative 3 pi over 4 radians? We can still measure angles negatively with radians, just like I showed you a little earlier with that negative 45 degrees. And the conversion is the same. It's not going to change the sign of your angle measurement or the direction in which you measured your angle. So we take our negative 3 pi over 4 times 1 radian. We know what 1 radian is. We know 1 radian is 180 degrees over pi. So the pi's will simplify. 180 divided by 4, probably a little easier to do than 3 times 180 divided by 4. So 180 divided by 4 is going to be, let's see, divide by 2 you get 90, divide by 2 you get 45. 45 times 3, well, that's going to give you 135. So negative 135 degrees. Let's think about the quadrants and see if it actually makes sense. So negative 135 degrees is negative 90, not past 180 though, negative 90, and then halfway between negative 90 and negative 180. That's almost like having a 45-degree angle starting from here and going downward. And that's exactly what we would get for something called a reference angle. We would get something very similar to that. So negative 135 degrees. Or we can think negative 3 pi over 4. Just do the same thing. Here's your straight angle of pi. If you cut it into 4 parts, that would be 1, 2, 3, and then 4. Now we're counting numerator, negative 3 of them. So denominator cuts it into 4 parts. Numerator counts it, 1, 2, 3. That's going to be still in quadrant 3 for us. So we cut 1, 2, 3, 4 parts and count 3. 1, 2, 3. That's quadrant 3. It's the same exact angle as negative 135 degrees, and they mean the same thing. We just got to be very good at going back and forth between them. And the reason why I'm spending so much time is so that you're starting to see them. You're starting to make the connections that they are measuring the same angles in 2 different ways, and that they're interchangeable. So we're going to do 2 more examples and then we'll be done. All right, we've got just a couple more examples. So let's get after these 2 and then we're going to be done. How about 7 pi over 3 radians? Now we're going to convert that to degrees, and I've done something kind of tricky. We can still measure more than 1 full rotation on this. It's okay to do that with radians as well, and we can still convert to degrees the same exact way. But let's start thinking about the quadrant here. Let's say I took my straight angle of pi and I cut it into 3 parts. That would look like 1, 2, 3. Now, if I had to count 7 of them, I'd have to think a little bit further than that. 1, 2, 3, 4, 5, 6. Notice that my numerator is counting more than the 6 parts that this denominator would cut 2 pi into. So what I'd be doing is thinking straight angle does 1, 2, 3. Another straight angle does 1, 2, 3. That's 6. And then 1 more. So if I had to count this, remember what we do. Your denominator cuts your straight angle into that many pieces. So first straight angle is 1, 2, 3. Second straight angle is 4, 5, 6. Multiples of 3. Next straight angle is 7. So we are going to end up in quadrant 1 here. This would be, cut this into 3 parts, 1, 2, 3. Cut the next straight angle in 3 parts, 1, 2, 3. Cut the next straight angle in 3 parts, and then go to the first one. So that's 1, 2, 3, 4, 5, 6, and then 7. So we're going to be 60 degrees above that zero, that first initial side when we do our conversion, but we're going to have gone 1 full rotation around there to get there, or pi over 3 past 0, but haven't gone 1 full rotation to get there. So we're still in quadrant 1. If we convert to degrees, that's 7 pi over 3 times 1 radian for sure. But that 1 radian is 180 degrees over pi. pies are nice. They simplify. 180 degrees divided by 3 is 60. 60 times 7 is 420. Well, let's think about that. 420 degrees, probably right away for you, is a lot easier to think about than 7 pi over 3, because this is nice and countable by 90s for us. So we can 90, 180, 270, 360, and then let's see, 420 is 60 degrees past that. So we've gone all the way around, and then 60 degrees puts us well into quadrant 1 at the same angle as that ended, but with a different type of a measurement. So we're still quadrant 1, we've gone 1 full rotation in 60 degrees, or pi over 3 degrees, or pi over 3 radians past that. They represent the same thing. Last one, 4 radians. You go, there's no pies. What are you going to do with no pies? Well, if you have no pies, it's not going to cancel, and you're going to probably end up with a decimal. So 4 radians, before we go any further though and do that, 4 radians, think about where that would be on a unit circle on this XY plane. Do you remember that pi is 3.14? Because remember that this is the number of radians. This is 0 radians. This is pi over 2 radians. That's like 3.14 divided by 2. This is pi radians. That's 3.14 radians. This is in terms of radians. So where would 4 radians fit? Well, if this is 3.14 radians, this would be 3 times 3.14 divided by 2. That's like 4.5, a little over 4.5. So 4 radians would be somewhere between 3.14 and close to 4.5, somewhere between that. That is what 4 radians would be. Now, that's in quadrant 3. Let's see if the same thing works out with our degrees. So 4 times 1 radian and nothing simplifies nicely. So in this case, yeah, you just take 4 times 180 and divide by pi. And what we're going to get is 229.18 degrees, if we approximate that. Well, where is 229 degrees? Here's 180, so going half of a rotation, but not as much as 270. Granted, this is much easier to place on this than 4 radians is on that, because we'd have to think about pi in terms of a decimal number that we kind of understand when we're putting 4 on there. I hope that makes sense. I tried to go above and beyond and give you some examples that are a little weird, but the main thing I hope that you have realized is that both are very valuable. We'll be using these in all of our math. Radians are what we typically use for formulas, so I'm trying to get you used to it. I hope that you understand the conversions, but most importantly, where they came from, where we understood that because the circumference of a circle is 2 pi r, and we divide by r, radians have pi's in them a lot, because it's a proportion of that circumference that we're sweeping out with a central angle. I hope that you notice the idea of cutting your straight angle with your denominator and counting it with your numerator. That's helped me out tremendously. I hope it helps you out. I hope I've done a good job of explaining this to you. I hope I've explained it well enough for you to understand. I hope that you're ready for another video. We're going to go for some real life examples here in just a little bit. Have a great day.